Good evening, everyone. I'm Anish Shambikar, PMRF and PhD candidate from Aerospace Engineering ISC Bengaluru. Welcome to this week's live interaction for the NPTEL course, Dynamic Behavior of Materials. The course code is NOC24ME102. In this session, we'll be covering the contents as well as a couple of examples to elucidate the concepts which were taught in the current week, that is week number 2. So this is the outline of topics that were covered. We'll quickly go through the concepts of each of these and supplement our understanding of the same with some problems. So elastic waves. What are elastic waves? So we first need to go back to stress waves propagation. So as we observed in the previous class, if a material undergoes some rapid loading f of t or some rapid displacement u of t, then sort of stress will be generated in the material, and then after some time it will move forward. The simplest example of the same would be, say, like a projectile hitting a target and then generating stress waves inside the target P. So stress waves can be categorized into three types depending on the amplitude. So you have elastic waves, plastic waves, and third one is the shock wave. All right. So how do we determine which particular wave is being encountered? You look at particle velocity UP being generated due to given wave, uh, due to say like passing stress wave. All right. So uh, if this particle velocity is sufficiently small, your amplitude of wave is proportional to particle velocity. If we take the simplest case of a say longitudinal wave, a particle undergoing oscillation. So this is the v wave velocity, and this is the particle up velocity, right? If this amplitude, if amplitude is less than elastic limit, we see elastic wave propagation. So if we go back, so what we could think of this is that in terms of stress strain curve, very simplified and understanding that here at some point you have a linear region of the stress strain curve, then a non-linear region following some yield, then a plastic region, and so on and so forth. What we basically mean here is that as the stress wave propagates, this particle UP it should oscillate within some amplitude, which in turn would generate some sort of stresses in this very small infinitesimal region surrounding the particle, and those strains should be under your elastic limit so that the material can go back to its original position. Elasticity by definition means that if the material is loaded and then when it's unloaded, if the material is loaded, it will undergo some deformation, and once it is unloaded, it will go back to its original position. So that elasticity of the material remains intact when the stress wave propagates through it. That would be your that amount of stress should be within some bounds. We'll later on, as we have seen in this week's lecture, but later on we'll also look at how the stress relates to the particle velocity directly using something called as acoustic impedance. So next up, we learnt about, suppose you have a cylindrical bar and another small object comes and collides it at some velocity v. Alright, so this would cause at t equal to 0, the two bodies would meet, and the momentum of my projectile would be my projectile will be carrying some momentum, and then that would be upon contact, some stress would be generated at the contact surface, following which a stress wave will start propagating inside the target as well as inside the projectile. If we just zoom into our target for the while, if I zoom into target, say this put some section in the target after some time t, after some time t greater than t1, which is the time required for the stress wave to reach this particular region. If I take a very small section, delta x, you can see that on both ends of this, you'll have some sort of compressive load, compressive stress acting, and compressive load acting, from which we can determine some compressive stress. Okay, if I want to do a free body analysis of this, I will first write down my assumptions for this fraud case. So we neglect strain and inertia laterally. What does this mean? That we do not consider any lateral motion of the bar like in this direction. Okay. So ideally, when the bar will be hit by a, say like a striker bar here, it will undergo compression along, say, the x-axis, and then it's then I think most of you would have studied Poisson effect in your undergraduate level mechanics of materials courses. So along the y and z axis, you can expect, because of the Poisson's effect, to have some sort of expansion along those axes. We are not going towards quantifying it, just I'm saying that at the moment, for this chosen bar, I am neglecting strain and inertia conditions, and inertia in lateral directions, and I'm also assuming uniform geometry and homogeneous material. Homogeneous basically means that suppose you have property of density, then rho at x1 and rho at x2 will be same. So if you have a material like this, then rho at this point and rho at this point will be same. We are not talking about isotropy yet. We'll get to that later. And we also assume that deformation within elastic limit. So if this is my small cross section, if I look at the forces, A sigma plus d sigma will write as dou sigma by dou x into dx plus some second order effects, which will basically neglect these higher order terms. So, and then you have some density rho. So if you're applying Newton's second law of motion, summation f to ma, what we get is A sigma minus of A sigma minus A times sigma plus sigma by dou x dx. The minus sign is coming due to compressive load, is basically rho a dx. Second acceleration is nothing but second derivative of displacement with respect to time. So if I simplify these equations and using Hooke's law, we have sigma is equal to E epsilon is equal to E times dou U by dou x. So combining this equation and this equation, what I get essentially is dou square U by dou t square is equal to E by rho dou square U by dou x square. This is the equation for elastic wave propagation in longitude in a long bar. Alright, so we have already chosen some assumptions to get to this point. And another thing you'll note from previous discussion as well, that this E and rho basically are stiffness and inertia terms. So you have basically again a ratio of the same coming up. From this we can write C naught is equal to root of E by rho as my wave velocity. Okay, a series of assumptions have gone in here, and what this tells us is where can we use this? If the material is homogeneous, if it has a constant cross section, if it's very thin, so that like the length dimension is much larger than your say like the radius of cross section, or diameter, rather the diameter of cross section. If you have those conditions being satisfied, then we can neglect the strain and inertia laterally, and uniform geometry and homogeneous material are already there. So from in this case, this is sort of a longitudinal wave propagating in an elastic bar, and this has some finite speed. C naught is equal to root of E by rho. If we move into a semi-infinite body and impact on the same, we see a much different picture. Suppose I'm dropping a projectile P, and this is my target. So once it reaches here, just show this in dotted line. At t equal to 0, it will impact, and then after that, for t greater than 0, elastic waves are generated. We are still in the realm of elastic waves for this entire for today's entire session. So the other types of waves will be encountered later. So what we see is we see we see three different types of waves. This is the longitudinal wave, also called as irrotational dilational P wave. Then another wave front that we see is the shear wave. This is called as the transverse distortional SHS V waves. Then apart from this, we can also see other types of waves depending on the material, specifically Stoney wave, which is also called as the interfacial wave. It occurs between two semi-infinite media, and then there are also something called as the Lamb waves, which occur in say layered media, or like something like plates, and where you have something on the both top and bottom surface. So there are series of like infinite number of Lamb waves generated. All these different we'll focus mostly on the longitudinal shear and a little bit on the Rayleigh wave. So all these waves, Rayleigh wave is typically confined to surface. Right here, Rayleigh wave. Rather than writing confined to surface, better way would be to write that its amplitude drops exponentially away from the surface. It decays r raised as 1 over root of r, which means that it travels a long time before it's on the surface itself, before its amplitude is too faint to detect, which makes it pretty useful in earthquake detection, wherein a seismic wave on the surface can travel multiple times around the globe and be detected. For the shear wave, you have 1 r square, sorry, r square, r decays as r raised to minus 2 decay at the surface, which is same for also longitudinal wave, and both decay by 1 over r deep inside medium. So if we are interested in studying some, if you are interested in studying some sort of wave interaction on the surface, Rayleigh waves you can see are pretty dominant because of their low decay on the surface, and uh, a lot of guided wave applications make use of this in especially in the non-destructive testing industry. And then you also have energy distribution depending on what sort of Poisson's ratio and all that you have. I think that part has also been covered in the class itself, wherein if I just write down the result, it is at mu equal to 0.25. You have energy distribution as energy distribution for the Rayleigh wave being 67, for the shear wave being 26, and just 7% for the longitudinal wave. Okay, next, uh, next topic that was covered was on basically how elastic waves propagate through in a continuum. So before we go into the dynamic part, let us quickly recap the quasi-static part. So suppose you have a continuum body. We look at a point O. Some boundary conditions are given to it, to this body, in terms of forces as well as fixed or free boundary conditions. If we zoom into this point O and I draw like a small material region around it, one, two, three, and center of this cube is O. At the center of the cube, we know like we already studied stress straight, so we can define the stress tensor to have like different components, sigma ij, with I being the force along xi and j being normal to the surface being xj. So if you are basically sigma 1 1, that would be force along x1 and plane is also along plane normal is also along x1. So this would be, say, sigma 1 1 plus half. Sigma 1 1 would be defined at point O, and if we find the value of sigma 1 1 at a distance half of delta x1. So this is geometry I should write. Half of delta x1 into dou sigma 1 1 by dou x1. Similarly, if I draw the straight here, it will be sigma 1 1 minus half dou x1 dou sigma 1 1 by dou x1. We are neglecting any higher order terms here. Similarly, I can draw here sigma 2 2 plus half delta sigma 2 2 delta x2 dou sigma 2 2 by dou x2. At the bottom, you can similarly write sigma 2 2 minus half dou x2 dou sigma 2 2 by dou x2. Sigma 3 3 inside and outside the plane, and then you have your shear component. So sigma 2 1 would be force along x2 and direction along, sorry, plane normal along x1. So be sigma 2 1 to sigma 3 1 plus those delta terms. So this is a very well-known stress cube diagram. You can find it in a lot of resources on either continuum mechanics or elasticity X. What we essentially have here is summation fi equal to 0 and summation mi equal to 0 for all I is equal to 1, 2, 3. So this is static equilibrium. Here both the forces or moments are balanced out. What this gives us is that the stresses on the opposite ends of the stress cube match with each other, and therefore you have a no variation in stress as a function of the material location. In case of dynamic deformation, what we have is suppose this is sigma 1 1 plus half dou sigma 1 1 by dou x1 delta x1. Here you have sigma 1 1 minus half dou sigma 1 1 by dou x1 delta x. Okay, so again, using Newton's second law of motion, so like we'll be only looking at using conservation of momentum. If we are only interested in seeing the forces along x1, if you are only interested in seeing the forces along x1, then you also have shear components on the top and the side faces. Okay, so if we sum up the different components, what we essentially see, we have gone through this derivation in the class, but if I have to rewrite the steps, it would be sigma 1 1 plus half dou x1 dou sigma 1 1 by dou x1 minus sigma 1 1 minus half dou x1 dou sigma 1 1 by dou x1. into area along x1, which is dou x2, dou x3, plus similarly adding the shear terms, adding the shear terms along x2 and along x3 will equate this to rate of change of momentum of this stress cube. So it would be rho times volume. Volume is dou x1, dou x2, dou x3. So this is mass into acceleration, dou square u1 by dou t square. Simplifying this, we end up with very simple expression, which is dou sigma 11 by dou x1 plus dou sigma 12 by dou x2 plus dou sigma 13 by dou x3 is equal to rho times dou square u1 by dou t square. We can similarly write another two equations for u2 and u3. If we rewrite everything in indicial notation, it's dou sigma ij by dou xj is equal to rho times dou square ui by dou t square. So this is what we get. In indicial notation, it's important that whichever index repeats itself, so either in the LHS or the RHS, twice. So an index has to repeat itself only twice. That index will be summed across. So here you have dou sigma I by dou sigma ij by dou xj on the LHS. So there is a repeat of index j, which means sum over, I should write j repeated twice, which means sum over j equals j belongs to 1, 2, 3. So all three terms that we see here are basically included in this indicial notation. Okay, for isotropic elastic solid, in a triaxial state of stress, triaxial meaning, I think it's self-explanatory. You can write sigma ii is equal to lambda delta plus 2 mu epsilon ii. Here I will write, here I will supplement the indicial notation with this statement no sum. This no sum would essentially mean that in this indicial, in this equation, there is no sum occurring even when indicial notation repeats twice. So this basically gives us sigma 11 is equal to lambda delta plus 2 mu epsilon 11. Sigma 22 is equal to lambda delta plus 2 mu epsilon 22. And same for sigma 33. This is what we get instead of sigma 11 plus sigma 22 plus sigma 33 on the left hand side, and similar terms on the right hand side. And for the shear component, you have 2 mu epsilon ij, where I is not equals to. We can define delta is equal to epsilon ii. This is sum, so I'll just write it epsilon 11 plus epsilon 22 plus epsilon 33. This is also called as dilatation. And generalized Hooke's law uses Lame's constant lambda and mu. If we substitute this into our earlier equation, we end up with an equation of motion which looks like, in indicial form again, lambda plus mu dou delta by dou x1 xi plus mu times grad square ui is equal to rho times dou square ui by dou t square. I going from 1 to 3. So this is the basic equation for a linear elastic solid with isotropy and homogeneity, and this is what is used to develop any like equation of wave propagation, elastic wave propagation in a continuum medium, so which is infinite, unbounded. A lot of interesting stuff happens when we have a boundary, as we have seen in this class. When there is a boundary, there is, and we'll revisit those concepts, there is an impedance mismatch which causes some part of the energy to come back from the boundary. So some pretty interesting stuff occurs there, which we can say use later on. Next, what we have is, if we do a partial derivative of this equation, dou by dou xi of lambda plus mu dou delta by dou xi plus mu times grad square ui is equal to rho times dou by dou xi dou square ui by dou t square. So in both LHS and RHS you have a repeat of index I occurring twice once we move it inside, and that basically means that both LHS and RHS have sums. Once we move this inside, what we get is lambda plus mu times, actually this is for simplification, so I can just write lambda plus mu times dou square delta by dou xi square. This is nothing but grad square delta plus mu times grad square dou ui by dou xi. This is nothing but delta itself, dilatation, is equal to rho times. If I move the dou by dou x inside the time derivative, so you have dou square by dou t square, dou ui by dou xi. Again, this also becomes delta, so we end up with lambda plus 2 mu grad square delta is equal to rho times dou square delta by dou t square. So this is equation for longitudinal wave in an unbounded isotropic material. If we can see that this form of equation is similar to like other forms that we have seen, including the string, spring, as well as the long thin bar. So if we look at the terms involved, this looks like the stiffness term, and this looks like the inertia term. Moving around, we get C longitudinal. I should write C longitudinal is equal to root of lambda plus 2 mu by rho. This is, you will notice, is this also called as the bulk sound speed, and this you will notice is not the same as the wave speed in a like a finite sorry in a thin rod. So like that was also a longitudinal wave, but there you had square root of e by rho. So we can work out what lambda and mu are in terms of e and nu. So Lame's constant lambda mu we can determine in terms of Young's modulus and the Poisson ratio. So from that we find that the velocity of, or rather the bulk sound speed, which is what we have calculated here, is larger than what we see for longitudinal wave propagating in a thin bar. Another type of wave that we see here is the shear wave. So in shear wave, there is no change in volume, which means your dilatation, we can directly set our dilatation to 0. And if we go back to our earlier equation, from this you can see that if the dilatation is 0, the first term directly goes away. So you end up with mu times grad square ui is equal to rho times rho square ui by rho t square. This is shear wave, infinite unbounded medium. So V shear wave I can write as root of mu by rho. And the third type of wave, we'll just touch upon this. It's the Rayleigh wave on the surface. For metals, we can write plus nu into V shear wave. This expression, if you are interested, I'll post a reference for this in the discussion forum for those of you who are interested into looking further into how this comes about. Can go through it. And usually for metals, nu is equal to 0.3, which gives P Rayleigh wave to be about 0.92 times shear wave velocity. So an example for the same. Suppose you have suppose you are interested in finding some, say, water reservoir inside soil, and you use a high energy explosive at point A, and then you have a seismograph seismograph at point B, which is 1,000 meters apart. This top surface is at a distance of say 200 meters. The high energy explosive at A is detonated at T equal to 0. He detonates. What do we see? Okay, I'll also write down some values. This is a rock with E is equal to 100 GP, not 1000 GP. Nu is equal to 0.4, rho is equal to 2.6 times 2 kg per meter cube. Okay, what we would see is when this explosive goes off, energy will start transferring through the medium. Longitudinal wave will reach here first, then it will bounce from here and will get to point B. There will be another way for the longitudinal wave to go. So here we'll have longitudinal wave along this path. You'll also have a longitudinal wave on this path. Similarly, a shear wave will also be seen along this path as well as the surface. And finally, you'll also have a Rayleigh wave propagating along the surface. Okay. I think I forgot to put this dimension x. Okay, I'll just write down this side length that we have is say 250 meter along this side. I'll name this point O. Another 875 meters along side O to B, and then 1000 meter for the side A to B. Okay, and from this we can determine that my longitudinal wave is equal to root of lambda plus 2 mu by rho, and my lambda is E nu upon 1 plus nu into 1 minus nu, 1 minus 2 nu, which is 142 GPa. My mu is E upon twice of 1 plus nu, which is 35.7 GPa, which gives my shear wave velocity is root of mu by rho to be around 3700 meter per second. My longitudinal wave velocity to be root of lambda plus 2 mu by rho, which is around 9000 meter per second. And my Rayleigh wave velocity is about 0.94 times my shear wave velocity. So once we have this, we can find out what seismograph B sees. So I'll write T and I'll write signal. So the very first signal would be directly from A to B. It has the shortest distance and the fastest wave is your longitudinal wave. So we'll first see at 0.11 seconds, you'll see the longitudinal wave. Then you will have like the path from AO to B, AO to OB is of the length of 1125 meters. So again, you will see longitudinal wave reflected at about 0.12 second. Third is third signal that we'll see is shear wave directly going from A to B, which is 0.27 second shear wave. If you look at the shear wave reflection, it will go from AO to OB, which will take about 0.30 seconds. And then there will be a Rayleigh wave going from A to B, which takes about 0.29 seconds. So a very simple and practical example of how the three different types of elastic waves that we see in a semi-infinite medium, how they are produced and how they can be used. So you can one of the way people researchers use this is they can detonate and then based on the amount of based on the times of arrival involved, they can estimate different kinds of parameters. So here, for example, we assume that the rock is homogeneous throughout. You could have a case where you have multiple layers of rock coming up. The depth will be larger for that, but then you have waves which are moving from one medium to another medium, when wave interactions become particularly important. So with that sort of introduction to this, we'll look at interactions. So suppose you have medium A and medium B. Assume that there is an incident longitudinal wave at the interface. Some amount of energy will be transmitted into the medium B as longitudinal wave. Another amount of energy would be transmitted in medium B as shear wave. At the point, you have another shear wave and the longitudinal wave being reflected inside medium A itself. So medium A and B have basically different sonic impedance or acoustic impedance. What this means is both medium when subjected to loading or other same amount of stress will show different uh, propensity for the stress wave to move forward in the material. Some will generate very large amplitudes. Some materials will have large amplitudes for the same stress. Others will have smaller amplitudes for the same stress. So the sonic impedance is defined as Z is equal to rho C. Rho is the density and C is the elastic wave velocity. So you can define it for different waves modes, and the way these different components are related and their angles are related. I'll just theta 1, theta 2, theta 3, theta 4, and theta 5. You have sine theta 1 by C1 is sine theta 2 by C2, which is sine theta 3 by C3 is nothing but C1 is sine theta 4 by velocity of the component 4, which is C2 dash, and sine theta 5 by C1 dash. So this you can notice is analogous to Snell's law in optics, which is based on principle that the time required for a, or rather the path that a ray will follow when it moves from one medium into another is such that the time required for the ray to follow that path is stationary, which means it does not change depending on what sort of angle the wave would take. The derivation is pretty straightforward in Snell's law. If you are interested, you can look it up in Wikipedia, and it's very straightforward. We are now interested in defining impedance for a thin bar under uniaxial stress. Okay, so you have a condition of normal incidence, longitudinal wave, which means theta is 0. Only longitudinal waves propagated, some stress, some force is applied which causes some stress. And if I look at one small thin cross section of the bar, what we see is initially before the stress acts on this portion, and then after stress acts on this portion, there is a change in momentum. So once the stress sigma acts for a time t, change in momentum equals impulse. So you have sigma into a area into time dt, for which this is the impulse provided to the thin cross section. This results a change in momentum of the rod. So you have this small mass is nothing but rho a into thickness of the cross section dx into up. Cancelling out the area terms, we get sigma is equal to rho dx by dt into up. Dx by dt would refer to the how much would refer to propagation of stress itself, the way we have defined it. Sigma in initial sigma stress acting on a thin cross section, and then after a while, after time dt, it will move slightly ahead by the distance dx. So you have this dx by dt is nothing but wave velocity rho c up. So from this we basically define our sonic impedance. Sigma by up is equal to z is equal to sigma by up is equal to rho c. In the case of a thin bar, So UP is the particle velocity inside this thin cross section. Yeah, like this. UP is this particle velocity. In case of okay, in case of a thin bar, we know that this C in turn can be written as for longitudinal wave C is e, square root of E by rho, which basically gives us Z to be root of E into rho, which means the impedance should depend both on your Young's modulus as well as your density. So again, both stiffness and inertia factor involved. What happens when wave hits a boundary? We are strictly sticking to rods. So the simplest possible case, this suppose I label this as my boundary. This is my medium A. This is my medium B. This is my elastic wavefront moving with velocity Ca. This is my particle velocity due to the stress wave propagation being up. This is the condition before, say at t less than 0. At t equal to 0, what we'll see is both there is some sort of transmission sigma t and a wavefront in B. There is incident stress, reflected compressive stress, and going back wavefront. So this is say t greater than 0. So at the interface between the two medium, what we have is, because the two medium have to be perfectly joined, there has to be continuity. Continuity at the interface. I should actually write the particle velocities also. UPI, UPR, UPT. Continuity at the interface means that like the displacements will be matching, which also means that the particle velocities will match, which gives us UPI, this UPR, this UPT. Another condition that we have is, because the interface is like interface itself has sort of like it's, if we approach it from medium A all the way near the interface, what force we'll get should match exactly the force that we have on the side of the interface coming from medium B. Think of it like limiting like limits when we say in calculus, x goes to 0 from the negative side and x goes to 0 from the positive side. In both of the cases, those forces must match, because that interface, hypothetical interface, is basically zero cross section, sorry, zero thickness, no mass negligible. So if there is a force mismatch, then the bars will like instantaneously split away. So if we approach it from the left hand side, force that we see is sigma I plus sigma R compressive. These are both compressive stresses, and this is equal to sigma T, which is compressive stress seen in medium B. Now if we use our previous equations relating stress and particle velocity, you have UPI is equal to sigma I by rho ACA. You actually here one more thing in the stress equation. Here we have assumed uniform cross section for both medium A and B. because we have assumed uniform cross section for both medium, we can directly write it as sum of the stresses. Otherwise, you have also to take area of those two different bars into account. Coming back to the particle velocity relation, we have UPI is equal to sigma I by rho ACA. UPR is in the reflected compressive wave is in the moving in the opposite direction. So we have a negative sign here, rho ACA, and UPT is sigma T upon rho BCB. If I just rewrite everything as rho I sigma I by ZA minus sigma R by ZB, sorry, ZA, and sigma T by ZB. If I take these equations along with this equation, what I end up with is, so using, let this 3, 2, this is 1. Using 3 and 2, I end up with a series of relations sigma T by sigma I equal to twice ZB upon ZA plus ZB. I have defined ZA and ZB as rho AC and rho BCB respectively. Similarly, sigma reflected by incident is minus of ZA minus ZB upon ZA plus Z. So these are two handy equations, and similarly, if we use equations 3 and 1, we end up with Z UPR by UPI, ZA minus ZB and ZA plus ZB, and UPT by UPI twice ZA by ZA plus Z. So what does this tell us? So we have three special cases. One, free surface, which is basically ZB is much lesser than ZA. If I plug this into our equations, I end up getting sigma transmitted is 0, sigma reflected is minus sigma incident, UP reflected is same as UP incident, and UP transmitted is twice of UP incident. So you have a bar like this, A, and then this is free. This is the stress wave. So once it reaches this free surface, it will, a reflected wave will come back, and at the, a reflected wave will come back here with the same, sorry, a reflected wave will come back. If the incident wave is compressive, reflected wave will be tensile. The interface at all times sigma t is 0, which means that the interface remains stress free and particle velocity is maintained. There is no change there. Another cases, if you have rigid surface, you have, which means ZB is greater than ZA, or ZB tending to infinity. This can be written as ZB going to 0. So you have sigma t is equal to twice sigma I. Sigma reflected is sigma I. UP reflected is minus UP I, and UP transmitted is 0. So if I draw this, this is the rigid surface A and this is the incident stress wave. It will reflect back from the surface, and it will UPT equal to 0, which means that this surface, as the name suggests, rigid, it's already a rigid boundary, but that surface will basically not undergo any deformation. If the incident wave is compressive reflected wave, will also be compressive. So from this, and then if particle velocity for the reflected wave will be reversed. Okay, so it will be out of phase with that. And if I take like a third special case, perfect match. If I take perfect match, and what you have is basically ZB is equal to ZA, which is basically one material itself. And if our equations and derivation is correct, what we end up getting is sigma T is sigma I, sigma R is 0, which means no reflected component, and similarly UPT is UPI and UPR equals 0. So you can see that these two terms will cancel out and this 2 will be 1, which means that the wave will transfer as it is. Simple example of the same could be, suppose you have aluminium and suppose you have steel. So 70 GPa, 2700 kg per meter cube, and total GPa, this is around I think 7000 kg per meter. Okay, so this is what we have, and what we want is C Z aluminum, which is C rho C aluminum rho aluminum. It's nothing but square root of 70 GPa. C is root of E by rho into rho, which is nothing but root of E into rho into 2.7 10 cube. So you have 70 into 2.7, 189 square root, which is about 13.75 into 10 raised to 6. Units would be meter per second, kg per meter cube, kg meter square second. And similarly, if you calculate Z steel, would be root of 210 10 raised to 9 into 7.8 10 cube. So 210 into 7.8 1638 square root of 1638 would be around 40.5 10 raised to 6 kg per meter. So then if a compressive wave is passed through a thin aluminum rod with same connected to a thin steel rod with same cross section, what do we have is, we can see that suppose sigma incident is 1 MPa, which means that U particle aluminum, which is sigma incident sigma incident upon Z aluminum, which is nothing but sorry, 1 second. I think this is right. So Z aluminum, Z steel. So if we want to see how much fraction of stress gets transmitted, it's 2 times Z steel upon Z steel plus Z aluminum, which is nothing but 40.5 into 281 divided by 0.5 plus 13.75, which is approximately 1.5. And if I calculate sigma reflected by sigma incident, it is nothing but 13.75 minus 40.5 upon 13.75 plus 40.5, negative of this, which is 13.75 minus 0.5, which is 26.75 upon 54.25, which is roughly 0.5. So whatever incident stress that we apply in experience inside the aluminum rod, about half of it we'll see a reflected pulse coming back with half as much stress, and a transmitted pulse with about 1.5 times as much stress going into state. Similar equations we can derive out for U particle reflected by U particle incident, which is ZA minus ZB. So 13.7 minus 40.5 on 13.75, sorry, plus 40.5, which is minus 0.5. So the uh, reflected particle will be like have a velocity, sorry, the reflected wave will have particle velocity which is reverse. And if we look at UP transmitted by UP incident, it's twice ZA, so 13 by ZA plus ZB, 10.75 into 0.75 into 2, which is 27.5 upon 54.25. Again, this also turns out to be about 0.5. So this aluminum steel interface essentially acts like a rigid interface, not rather rigid interface, but going from a low impedance material to a high impedance material. So as the ratio between transmitted material impedance to the original material impedance ZB by ZA, as that becomes very high, much larger than 1, so like 10, 20, 100 or so, this will start mimicking like a rigid interface. On the other hand, if it becomes much smaller than once below 0.1, 0.05, will start uh, it will start behaving similar to a free interface. Another problem that we could look at, I'll just leave here, is what would happen in the case of a stepped rod. So suppose you have the same medium, aluminum in both A and B, or same medium A in both cases. What would happen here? So we already have seen in the derivation that whatever force this boundary has between the two interfaces, that needs to be matched. So instead of initially for same cross section, we had the equations sigma incident plus sigma reflected, sigma transmitted. Here we would have for differing cross section. If we ignore, we'll ignore like how the force gets transmitted and what happens to this small free surface on the either side of the rod. If we just do a simple continuum analysis, what we end up with is sigma I plus sigma R into area of A should be equal to sigma transmitted into area of rod B. And then again for particle velocity, same equation, UP incident plus UP reflected, same as UP transmitted. From this, we can work out what happens to transmitted and uh, transmitted stress, as well transmitted and reflected stresses, as well as their respective particle velocities. The only important thing to note now is that there is an area term which has to be included along with our impedance terms. So from this, I think you can also work it out. It's pretty straightforward. Okay, so I think this covers most of the stuff that we had in this week. And if you have any particular concept that you want me to revisit, I could do that now. Okay. If not, then we'll call it a day. And I hope you learned something new. Uh, and we'll meet again in the next class. Okay. Thank you.